Logic gates. Computers send information in the form of ones and zeros through transistors switching the voltage on and off through its circuit. These ones and zeros are used in complex calculations to provide more useful outputs for the computer to carry out tasks such as adding, subtracting, multiplying, dividing, etc. Computers transform inputs of 1 and 0 by using logic gates. There are many different types of logic gates that output different results based on different combinations of inputs. For a computer to add the base 10 numbers, these are the numbers we deal with in normal everyday life, must be converted to a binary string of ones and zeros, it's over here, to put through a series of logic gates. So when you add 85 to 181, you get 266. This is the representation in binary of the number 85. This is the representation of number 181, and this here, and there are rules for adding these two to get this answer, which when you translate it back to base 10, you get 266. So computers work here, humans work here. Logic gates are made by stringing together transistors in a specific useful sequence. The transistors control the flow of electric current through the logic circuit, switching them on and off to process information. By connecting these transistors, an infinite amount of logical circuits can be made, well, nearly infinite. But in reality, it is easier to work with a select few in order to make computers run and perform tasks. There are 7 basic types of logic gates that we will explore, which can be combined for more and more complex functions. NOT, AND, OR, NAND, NOR, XOR, and XNOR. Their functions will be explained next. But first, here is a circuit diagram for one logic gate, the NAND gate, at the transistor level. Combining 2 of these gates in series yields a different operation. So we've got a transistor here, we have several resistors, and then we have a power supply over here, and it looks like we have a diode over here. A truth table shows the possible outputs of a logic gate when given all the possible combinations of inputs. The possible inputs are listed as zeros and ones because we're working binary. 0 corresponds to no voltage, and 1 corresponds to high voltage. The output is the signal that comes out of the logic gate. So what are our combinations? Well, 0 can be paired with 0, 0 can be paired with 1, and then 1 can be paired with 0. Now notice the order counts here. And then of course 1 can be paired with 1. So these have the same inputs, just reversed. Then it tells you what the output is. The first 3 give you outputs of 1, and the last one gives you a 0. The most basic logic gate is the inverter, also called the NOT gate. An inverter will output the opposite to the input. That's pretty straightforward. And once again, the relationship of inputs and outputs of logic gates is expressed in truth tables. Each of the basic gates has a unique symbol used to represent it in circuit diagrams. The NOT gate is easiest to spot because it has only one input and one output. Input, output. And if you input a 0, you get the opposite. You get a 1. Input a 1, you get a 0. We'll cover the AND and OR gates on one slide. Both have 2 inputs and 1 output. The AND gate will only output a 1, which is true when both outputs are true, or 1. So let's make sure that works. Yep, 0, 0 gives you a 0 because neither one is a true input. 0, 1 gives you a 0 because you only have one of them true. This one, you only have one of them true. This is the only one that gives you a 1 for an output because both inputs are 1s. Now let's go to the OR. Well, if you have 0 and 0, that outputs a 0 because neither one is a 1. 0, 1, well, this is a 1, so your output will be a 1. 1, 0, same thing. And if you have a 1 and a 1, that will also give you a 1. Now we have 2 negative gates here, the NAND and the NOR gates. The NAND, which is short for not AND gate, will output a true when both inputs are not true, or false. Here's the symbol for the NAND gate. Then the NOR gate, which is not OR, will output true when both inputs are false. And that's its symbol right here. So if you have 2 falses, we'll talk false and true this time instead of zeros and ones, you get a true. If you have a false and a true, you get a true. And if you get a true and a false, you also get a true. The only time you get a false output is when you have both true inputs. And then similarly to the OR, except reversed, if you have two zeros, now we'll go to numbers, two zeros will give you a 1 as an output, a 0 and a 1 will give you a 0, a 1 and a 0 gives you a 0, and finally two 1s also give you a 0. So this is the opposite to the AND and the OR gates. The XOR and XNOR gates. First, the XOR gate, where the X stands for exclusive. The XOR gate will output a true only when one output is true. So here's its symbol. So let's look here and we'll go true, false. So true is going to be a 1, false is a 0. So in this case, you don't have any 1s, so you get a false output. In this case, you have one true, so you get a true output. That's good. Here, you have one true, and that one is not true, so you get a true output. Here, they're both true, but you can only have one true to get a positive or true output, so you get the 0, which is false. The XNOR, exclusive NOR gate, will output the opposite of an XOR gate. So here's our table here. We have two falses. Now for a NOR gate, you would have gotten a 0 as an output. Here you get a 1. It's opposite. So you have a 0 input here and a 1 here. Once again, you get the opposite of the XOR gate, so you get a 0. And this follows the same logic as this one, so you get a 0 again. And here you have a 1 and a 1. That gives you the output of a 1. Logic gates are the basis for Boolean expressions. These are a type of mathematical equation that can be used to determine the output from a number of different inputs. In the 19th century, an English mathematician named George Boole worked on mathematical logic, algebra, and the binary number system. His efforts led to the development of computers, and it's why Boolean algebra is named after him today. Boole and Augustus de Morgan, another prominent mathematician, formulated theorems in Boolean algebra that simplified and found equivalent Boolean expressions. In computer chips and microprocessors, logic gates are packed into integrated circuits. When a certain minimum voltage is applied to one of the inputs, the gate responds with a corresponding output, either a 1 or a 0 depending on the type. And you can see here, hopefully you can see here, here are the logic gate symbols that we went over on the previous slides. In a standard integrated circuit with 1 to 16 pins, you got 8 on this side, then 8 on the other side, about 6 gates can be accommodated inside. This IC is connected to an external circuit on a circuit board to perform the appropriate logical function.